In today's class, we'll study more about Coulomb's law. So just to recap what we studied in the last class, that when we have two charges, suppose Q1 and Q2 are two charges, and the separation between the two charges is R. So from Coulomb's law, we came to know that there exists a force, and that force is electrostatic force or Coulomb's force, and the magnitude of this force is 1 over 4 pi epsilon naught Q1 Q2 over R squared. So this is the magnitude of the force that exists. Now what would happen if you have number of charges? So suppose we have number of charges here. Suppose we have here Q1, we have Q2, we have Q3, and we have n charges, suppose Qn. And here we have, suppose Q, and we want to know, or if we label it in this way, suppose we label it in this way, suppose this is Q1, and this is Q2, Q3, Q4, and it goes to Qn. And now we want to know what is the resultant of the force on 1 because of all these charges. So we know that it's a vector quantity, so there's the charge here, this is going to interact, and the force, and these two are of similar nature. So suppose the force is going to be force on 1 because of 2 could be written in this way. Similarly, if this is the charge Q3 and this is the charge Q1, we want to know what is the electrostatic force on Q1 because of Q3. Both are of similar nature, suppose positive, positive. So we'll have this direction of the force, that is force on 1 because of 3. We'll write it in this way. Similarly, in case of this is the Q4. So what is the force on 1 because of force, because of the charge Q4? We'll draw here, and we'll have representation like force on 1 because of 4, charge 4. Similarly, if this is Qnth charge, because of nth charge, what is the force on Q1? What is the force on Q1 because of nth charge? So we can draw a line here to represent the electrostatic force direction would be force on 1 because of nth charge. So this is how we can draw the vector diagram. So what is the net force we want to know? We want to know what is the net force on this. So we want to know what is force on 1 because of net charges. There's something that we'll talk about, and that's known as principle of superposition. So let me write it here. So we'll be using principle of superposition. Principle of superposition. In simple terms, it says that these interactions are independent. So the interaction between 1 and 2, the interaction between 1 and 3, the interaction between 1 and 4, and the interaction between 1 and n, nth charge, these are all independent. And what is then the net? The net is that we need to act them vectorally to get the net charges. So what it is saying, this principle of superposition, it says that force on 1 because of net would be equal to the interaction between each independent pair. So it would be the vector sum of F12 plus F13 plus F14, and it would go on until F1n. This is what the mathematical expression of principle of superposition that is applied here, and it works. It works here. How can we then represent this in terms of the Coulomb forces, that is the quantities involved in Coulomb forces? So let's take those notations. So if you want to take Q force 1, 2, we can write this is going to be Q1, 1 over 4 pi epsilon naught, Q1, Q2 over R. And if you want to represent this vector array, right, these are all vectors. So this is the magnitude. Now you want to represent this vectorally. What this is the magnitude, we are going to multiply this with a unit vector in this way. So this is going to be then for 1, 3, 1 over 4 pi epsilon naught, it would be Q1, Q3 over R square. Now here, this is 1, 2, this is 1, 3, and unit vector here we'll write 1, 3, unit vector this, plus 1 over 4 pi epsilon naught, Q1, Q4 divided by R14 squared, and then we can write it here, unit vector 1, 4. It would go on until 1 over 4 pi epsilon naught. We can have this as Q1, Qn divided by R1n squared, and then we'll multiply this with unit vector 1n. This is how we can represent this vectorally. F1 net. So let's take these common, these quantities, the quantities which are common, let's take it out. So we can write it like Q1 is coming in all the terms, 1 over 4 pi epsilon naught is coming in all the terms, so we can take this common. Suppose we write it here Q1, and 4 pi epsilon naught could be taken out, and we can represent this in terms of summations, right? So we can suppose say I is equal to 2, and from 2 to n it varies, and we can write it here Q is there, Q2, 3, 4, it will go until this way, so this is Qi, and over R1 and I squared, and then here we can write R12, which is 1I epsilon unit vector. So this is how we can represent F1 net using principle of superposition. So we understood from this principle that all these charges, if there are number of charges, they interact independently, and then if you want to find for any particular charge what is the net force on this because of all the charges that is involved, then we'll be adding all those interactions independently, and the vector sum of those forces is going to give you force on that particular charge because of the net charges that is present here. So it's very important principle that is deployed here to figure it out, what is the net force on charges when multiple charges are there. You can take note of this. So you have taken note. Let us move forward. Let us now try to understand and summarize everything that we have understood until this point. So first thing that principle of superposition holds in this situation, and we are talking of what? We are talking of electrostatic forces. So first fact that we learned about, that like charges are going to repel, unlike charges are going to attract. It uses the superposition principle holds. Another fact is electrostatic force. Electrostatic force is a conservative force. Is a conservative force. And the equation that we have used until now was when the separation is between the charges, we assume that there is a vacuum or air. What if there is an intervening medium? So if there is an intervening medium, suppose you have Q here, Q1, and you have Q2 here. Let's take an example. The nature is similar, and the distance is R. The distance is R. So what's going to be the forces? So there would be forces in this direction, so we can write force. Force on 2 because of 1 would be in this direction. Force on 1 because of 2 would be in this direction, right? All right. What if this is, we have assumed vacuum. What if there is no vacuum, but we have a dielectric, any insulating material, right? So if there is any insulating material instead of vacuum, if we have here a dielectric medium. So what is dielectric medium? Any insulating material, if it is available here between the charges, then what would be then now the Coulomb's equation for the force that exists? It would be repulsive, but here we are going to understand a very important concept, that this dielectric medium, if we consider the permittivity of this intervening medium to be epsilon, intervening medium is epsilon, then the force that exists would be 1 over 4 pi epsilon q1 q2 over r squared. What is the relation then between this epsilon and epsilon naught? So this is, epsilon is absolute electrical permittivity of the medium. And we already know what is the absolute electrical permittivity of free space. We denote that by epsilon naught. Now there's a relation that's known as relative permittivity. Now this relative permittivity is the ratio of these two. And this relative permittivity has a name which is known as dielectric constant. So the notation used is K, and this K is known as dielectric constant. Dielectric constant. So what exactly is happening? What effect it's going to produce? The effect is the force gets reduced by a factor K. The force, because of this introduction of this medium, gets reduced by a factor K. So this F is equal to F naught over K. So this is very important relation. The force, if F is the force, when you use the medium, a dielectric medium, then the effective force, this gets reduced. So this F naught would have been more, because of this dielectric, it has got reduced by a factor K. And the relation goes that this K is known as relative permittivity. Another name is dielectric constant, so this we can also refer to as relative permittivity. And this relative permittivity is epsilon, which is absolute electrical permittivity of the medium, over absolute electrical permittivity of free space or vacuum. Extremely important relation, so that you can remember for numerical problems. Take note of this. Now we'll try to apply this concept in a situation when you have two charges and you have another charge placed. Then we'll try to understand this concept there using a question based on principle of superposition. So take note of this. All right. Let's take an example. Suppose you have two charges Q1 and Q2. And you have both the charges placed on x-axis. So you place both the charges on x-axis. And now we have, let me draw this again, just a moment. Let me draw this again. Suppose we take the axis in this way, and you have here Q1, another charge is placed in this in the close proximity, and you have here charge placed on the x-axis Q2. The distance between this is R. Let's take R. And we are given certain values. Now we need to find first thing that what would be the force between these two, and then we'll introduce third charge here in different locations, and then we'll try to use principle of superposition to get the answer. So this is how we get the values. So let us take the values here. The values of the charges could be, suppose Q1 is given 1.6 times 10 raised to the power minus 19 coulomb, and Q2 is given 3.2 times 10 raised to the power minus 19 coulomb. Now we want to find what is the force F12 here. What is the force here? Force on 1 because of 2. So we know this. The magnitude of the force goes 1 over 4 pi epsilon naught times Q1 Q2 over R square. And R is also given. R is suppose 0.02 meters. Right? So let me check the question. It's 0.02 meters. Q1 is given, Q2 is given, great. And we need to find what is the force on 1 because of 2. So first thing we need to figure out what would be the direction. We know the direction is going to be in this, right? This way. Force on 1 because of Q is going to be in this way. Why? It's going to be repulsive. Both the values are positive, right? So it's going to be a repulsive force. So if you put in all the values, let us put in all the values, we'll be getting 1 over 4 pi epsilon naught is approximately 10 raised to the power minus 10 raised to the power 9. 9 times 10 raised to the power 9 times Q1. Q1 is given 1.6 times 10 raised to the power minus 19 coulombs. All right, and this multiplied by 3.2 times 10 raised to the power minus 19 coulombs again. And then this is divided over, it's over 0.02 whole squared. This is the magnitude of the force. So whatever force would come, it will be in newtons. All those are SI units. So if you evaluate, let me use my calculator for that. So if you check the answer, it comes out to be approximately 1.15 times 10 raised to the power minus 24 newtons. 1.15 times 10 raised to the power 24 newton. So what's going to be the direction? The direction is going to be negative I cap, right? So the direction is negative I cap. This is the direction. So if you place this negative sign here, this is the value we get for force on 1 because of 2. So we have used unit vector notation here to determine or to denote what is the direction. Now we are going to place another charge of the opposite nature somewhere here so that everything remains in equilibrium. Which means that when you place another charge, the net forces are such that no charges are going to go anywhere. They are going to stay there in equilibrium. So take note of this, and then we'll move ahead with this configuration wherein we have Q3 charge placed again, and the value of the Q3 charge would be 3.2 times 10 raised to the power minus 19, but with the negative sign. So let us take situation 1. Situation 1 is when you have another charge placed here, somewhere here, and the distance is now, suppose I place Q3 here, and this is negative Q3. Okay, we'll write that the value there later on. So it's Q3, and the distance from Q1 is 3/4 of R. The distance is 3/4 of R. Now all the three charges are in equilibrium, which means that force on this because of 2 is in this direction. Force on this because of 3 is going to be in this direction. It's going to be in opposite direction. So we have introduced situation 1, case 1, Q3 equals negative of 3.2 times 10 raised to the power minus 19 coulomb placed at a distance. At a distance 3/4 R from Q1. So we are interested to find what is F1 net. So here F1 net would be equal to, by principal theorem, superposition theorem, it's going to be F12 plus F13. We already know what is F12. Let's try to find what is F13. So let's find the magnitude first. It's going to be 1 over 4 pi epsilon naught Q1 Q3 over, what is the distance? It's 3 by 4 R. R is 0.02 everything squared. This is going to give you the magnitude of the force. So let us place the values here. It comes out to be Q1 is 1.6 times 10 raised to the power minus 19 times. Then it comes out to be 3.2 times 10 raised to the power minus 19. And this is going to be the value, the magnitude, the values is going to be in Newton. If you calculate this, it should come it's coming around 2.05 times 10 raised to the power minus 24 Newton. Now what's going to be the direction for this? What should be the direction? The direction is going to be I cap, right? The direction is going to be I cap. So therefore, what is F1 net here? So F1 net would be equal to, we got earlier, the value was 1.15 times 10 raised to the power minus 24 and this plus this value 2.05 times 10 raised to the power minus 24. So this was negative, right? And I cap. And this is positive I cap. So eventually we need to subtract this. So if you subtract this, it comes out to be so you can use this value 9 times 10 raised to the power minus 23 Newton. And what's going to be the resultant direction? It's going to be I cap. Right? So now we have got this value F1 net, which is 9 times 10 raised to the power minus 23 Newton I cap. So we now know this is what the force because of 3 charges when all the charges are in equilibrium.